In this video we're going to talk about the Poisson distribution, and this is again a discrete distribution, and the random variable that we're interested in counts the number of arrivals in a unit time or space or volume. So we assume that the events occur randomly and independently over a amount of time. So for example, we'd say if time's going by this direction, we say here's 1 unit of time. What we're going to do is we're going to count the number of arrivals. So here we've got 1, 2, 3. Here during this time, 1 unit of time, we have just 1, and so forth. So examples of this might be hits on a web page. How many hits do you get per hour, per day, per minute, per year, that sort of thing. Or another example would be, this doesn't just have to be with time. You could have the number of defects in a square yard of material that's produced on a machine, on a loom, and that sort of thing. So the Poisson is a very useful distribution, and there will be homework questions asking you about it. And if we let x equal the number of units that show up, the number of events that occur per unit time, then x is this random variable, and it's one that depends on the unit of time that's observed, when the unit of time is observed, I should say. So for example, we could say x is equal to 3, or x is equal to 1, or x is equal to 5. And these all depend on when the randomly chosen unit of time happens to fall. So the Poisson distribution has one parameter, it's lambda, and lambda tells us the average number of occurrences or arrivals per unit of time, or could be space as well. The characteristics of the Poisson distribution are, we've got a single parameter, that's lambda. Again, that's the average number of arrivals, and the PDF is written as this formula right here: lambda to the x, e to the minus lambda over x factorial. And the CDF is just the summation of that, and so we're not going to write it out. But the PDF and the CDF can both be found in Excel using the function Poisson.dist, where you put in x, you put in lambda, and then the only difference between these two is whether it's cumulative or non-cumulative. And the domain of x, the values that can go into x, are 0, 1, 2, 3, 4, 5, all the way up to infinity. So there's no upper limit on this. It can go all the way to infinity, but it can go there in a countable manner, which means this is discrete and not continuous. So the average value is lambda. That's the same lambda we have up here. The standard deviation turns out to be the square root of lambda. So here's an example. On Thursday morning between 9 and 10 a.m., customers arrive and enter the queue at Oxnard University Credit Union at a mean rate of 1.7 customers per minute. So every minute that goes by, on average, there's 1.7 customers that show up. So we can write down the probability density function for the number of arrivals per minute, and we do that by taking lambda to the x, e to the minus lambda over x factorial. So lambda is 1.7, we're going to plug that in here, and note that the average value is 1.7, and the standard deviation is the square root of that, 1.34. So we can talk about compound events, in other words, cumulative probabilities that can be calculated just by summing the probabilities for different values of x. For example, we could say, what's the probability that 2 or fewer customers will arrive in a given minute? That's just going to be the probability that x is less than or equal to 2, so 0, 1, or 2. And we can find those values in Excel if we like. So now we've got the Poisson distribution. We can say here's 0, 1, and 2, and let's say this is equal to the Poisson distribution. X is that thing, mean is 1.7, cumulative is 0. So we're going to add these things up. So first we'll copy them all and then add them up, and we get the same numbers as what we have here. The easier way to do this, first let's get the sum. There's the sum, and if we use the cumulative, this is going to be Poisson dist. Mean is X is 2, mean is 1.7. Now we want cumulative. So if we do that, we get exactly the same number here as here. This was a lot easier, a lot quicker. So we could ask the question, then what's the probability of at least 3 customers? And this gets to be a little more interesting because X can go from 3 all the way up to infinity. Now, if you were to try that in Excel, you would say, so this is equal to the probability X is less than or equal to 2. And here we're going to say probability that X is greater than or equal to 3. So one way we could do this is start with 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, and 20. That ought to be big enough. Change that back to 17. Now we're going to copy this, plug it in, and paste all the way down here. And here we see that we've got 3 times 10 to the minus 15. So that's effectively 0. So at some point, what we're adding on is going to be so small it's not going to make a difference. So we could sum these things up if we wanted, or we could just take 1 minus this number, and we should get 0.24. So if we say this is equal to the sum of these numbers, you'll see we get the same thing. And sure enough, that's what we get over here as well. So that's what we've got for the Poisson distribution, and you'll be using this distribution in some of the homework questions. So don't hesitate to send me email or ask questions if you run into trouble on the homework. Okay, we'll see you in the next video where we talk about the hypergeometric distribution.